Okay, so we're using an AC circuit here, but this would apply to a DC circuit as well. And we're going to be looking at series, parallel, and then combination circuits as far as this goes. And one of the things you need to definitely understand, if you don't have a good handle on it at this point, is the difference between opens and shorts. And shorts can oftentimes be catastrophic, but not necessarily. If you short across your car battery terminals, that would be pretty catastrophic. But in an electronic circuit like we've got here, it could be catastrophic, or it could be just something we need to troubleshoot because it's not behaving correctly. So let's talk about a short. A short is a connection of 2 points that are not intended to be connected. So if I short across the source, obviously we don't want to short a source. Like I said, if we go across our car battery and short across that, which is a DC source, we would have sparks flying and things melting and potential for some other dangers there too. And if we, by that same token, go into our outlets in our home, and please do not do this, but if we stick something in both prongs like a gem clip, besides the prospect of being shocked or electrocuted, we would be creating a short, and something would definitely happen that we didn't want to have happen, and it would be more on the catastrophic side of things. But we see here a little circuit here, and we're going to, just for the sake of argument, say this is 12 volts AC. We can tell it's alternating current because we see the current path alternating in the pictorial here. And we can even hover over it and see what our current is. And of course, I can slow this simulation down a little bit so we can see that in a more slow fashion so we can see it peak, and it takes a minute to dial this in. But let me hover over this, and the peak will be at some point. So we're watching current in here, and it's still fairly subjective. 70, 80, 90, 100, 110, somewhere around 110 milliamps. Now we can do the math on that. We can take, let me make sure I've got my source set to 12 volts. That's another, and the reason I'm setting this to 6 is I think this is a peak to peak value, but I'm not sure. We'll find out. So let's see, 12, working some calculations here. 12 divided by 45 equals, so it must not be peak to peak. I couldn't remember on this particular waveform if it was or wasn't, but I'm going to find out here real quickly. So let's see what our current goes up to. Looking here. About 266. So yeah, that's right. So 266 milliamps is the approximate. And the reason it's changing is because we're slowing down the simulation and we're seeing current in fractions of a second. Obviously, in the real world, we would see an average of that. And we're okay there. So all is good with that. And so we're going to talk about what happens if we short certain components and if we open certain components. Opens are real easy. Let's start with that. We know that a circuit means we make a path from our source through some components and back to our source. And it's not necessarily circular in this picture, but it's an around the bend circuit here that we've got. And so if we break that circuit, we're going to have no current flow. And it doesn't matter if I remove this wire, and I'll cut that, but notice my current stops right away. We have opened our circuit. And that open can come in many forms. It can come in a pathway that should be there going away like it did when I took that out. It can go with a resistor missing. I'm going to take out this resistor, and you see the exact same thing happens, and our current is interrupted. So in a series circuit, an open will always lead to loss of current flow. We'll have no current flow because we don't have a full circuit. We don't have a pathway leaving our source and back to our source. So that's the easy one. That's what an open is. And it's real simple to understand, hopefully, for you. And now we're going to talk about shorts. Now, if I come in here and add a wire, I'll do that just for grins and giggles. I've never really tried it on the simulator, but I'm gonna actually short across our circuit. If I can figure out how to do this, across our source, I should say, and we'll see that what it actually has in the bottom left. I'll scroll down where you can see it. Voltage source wire loop with no resistance. So even the simulator, I'll keep it there so you can read it. Even the simulator I'm using is going, hey, this ain't good. So we don't typically short across our sources, or big, bad, spectacular things happen. When things fall across Georgia Power lines and create a path from there to ground, that's a short. That's an unintentional short, and it is not cool. So we typically don't short across the source. Now we've got a short, again, is basically bypassing something that not meant to bypass. Obviously, we're not meant to bypass our source and connect it to itself. Now we've got 3 resistors here, and I'm going to make it start running again. And I'm going to short across a resistor. And when we short across a resistor, we're essentially taking that component out and replacing it with a wire. So I'm going to draw, and I'm going to add a wire. I'm going to do my best. Yep, here we go. And add that in. And what you're going to see, notice there's no current flowing through this 10 ohm any longer. Remember, current always seeks the path of least resistance. So current's trying to flow along, and it says, ooh, there's a little bit of resistance here, but look, I'm wide open to go here. And it's going to take the path of least resistance. So in all intents and purposes, it's as if that 10 ohm is no longer there. We have bypassed it. So that is what a shorted component looks like. I'm going to add it back in because it's the same with it there or not, because notice we have no current flow. And if we look at our resistance, you're going to see that our overall resistance has, excuse me, if we look at our current, not resistance, overall resistance has decreased, but overall current has increased. So resistance is opposition to flow of current. So if we decrease that, then we're going to increase our current. We're somewhere around 340 milliamps at this point. That's a little bit off your screen. Let me get it where you can see the whole thing here. So about, if you watch it, around 342 milliamps is the peak value there. So again, it's as if this circuit is no longer has that 10 ohm there on the far right. So basically, we went from 45 ohms resistance to 35. So if we say 12 divided by 35, we'll get 342 milliamps, which is exactly what we're seeing if we can watch that fast moving number there. So now I'm going to take that out, and we're going to see the same thing is true if we bypass this 25, except our values have changed. And I'm leaving that one there because I'll need it. So we're going to short out our 25 ohm here. And notice no current flow through the 25. We'll watch our current, and we're going to see it's going to change to about 600 milliamps. So let's watch it one more time just to make sure. Yes, somewhere around 600 milliamps. So if we take 12 volts and divide it by 20 ohms, we get 0.6 amps or 600 milliamps. So, and again, it's as if this component no longer exists. And notice I took it out. We're going to watch our current. We're going to see it stays at 600. Current's going. I'll undo my takeout. The current's going, hey, here's a path that has absolutely no resistance. Same thing you would do if you were walking in the woods and you saw this path that had a whole bunch of sharp stones and foliage and everything in your way, and you saw this little cut around, you go, I'm not dumb, I'm going this way. Well, from a physics standpoint, that is exactly what current does. So take a look at this. Before, we shorted out this 10 ohm. So our resistance went from 45 ohms down to 35 because this 10 ohm was no longer here. Now we've shorted out this guy, and our resistance has went down to 20 ohms. Can we have a short across more than one component? Yes, absolutely. Let's do that. So I'm going to cut this wire, and I'm going to add a wire from here to there and here to here, and notice no more current flow through both this 10 and 25. Let's see what our current is up to though as we watch this. So 1.1, about 1.2. Let's watch it one more time. 1.1, 1.2. Yeah, I saw 1.2. So let's do the math. 12 volts divided by 10 ohms is 1.2 amps, or 1200 milliamps if you prefer the milliamp, but 1.2 amps would be the proper thing there. So can we have a short and still have a semi-functioning circuit? Probably not functioning the way we intended it, no, but still having current flow, still having some movement of electrons in the pathway. If we short across that source, we will see something catastrophic. The simulator goes, no, I'm not taking that. And let's notice something here. I'm going to cut this wire right here, and I'm going to add a wire right there. And if I draw this to here, I get that same, I'll let you see it, I get that same, whoops, I hate it when I do that, I forget to hit my escape key. I get the same, I'm trying to move the screen, guys, sorry, voltage source wire loop with no resistance. The reason for that is shorting from this point to that point is really the same as shorting this point to that point, or this point to that point. Electrically, when I short it across this source, I'm doing the same thing here, because my source has a pathway right there, my source has a pathway right there, and I've essentially installed the same short that I did to start with, which I said was catastrophic. Now you can even have a hodgepodge of shorts, and let's talk about that. I'm going to take this wire out, and I'm going to, let's draw a wire. I'm going to short here. Now this would be two unique shorts and wouldn't always happen too often, but yeah, can it? Sure. And that's what we're seeing here. So effectively, I've done away with my 10 ohm and provided it with a path of least resistance. I've done away with this 10 ohm, provided it with a path of least resistance. Let's see our current. Let's see what we're maxing out at. 200, 3, and 4, 480 approximately. Let's watch it one more time. And I'll let you see that's in milliamps. Let me move it. Let me get back on the circuit. I'm looking there in the lower right. Yep, 480 milliamps. Let's do the math. So let's say 12 divided by 25 is 480 milliamps. So that's opens, that shorts in a series. It's pretty easy, but wanted you to see it. And that applies in DC and AC. We change the characteristics of the circuit one way or another. If we're shorting across one component where there's multiple in a series, we're going to see the overall resistance drop, and we're going to see current go up, because if the resistance drops, current is going to go up. And that's exactly what we saw. And again, this applies to DC and AC circuits.